Okay, thoughts on the word explicit?
Explicit. We're thinking like music, it's not censored, so like there's no restrictions. So then we're thinking implicit, maybe it's like the opposite. So there's restrictions.
Okay, so like restricted versus not restricted. Okay. Other thoughts?
Partially right.
What?
I was partially right.
I haven't said like who's right. I mean, there's multiple meanings, right? I didn't say you're wrong. I didn't say you're right. Okay, we're just talking. Any other uses that for explicit other than music that you've heard? Oh, if you do something explicitly, you do it on its own, like one time. Okay. We're going to come back to that. If I ask you to take the derivative of this, don't write it down, but if I ask you to take the derivative of this, is there an issue?
Yeah.
What's the issue, Eli?
Y is
Y is squared. Well, could we solve for y?
yeah. Oh, then it'd be plus or minus.
Okay, so we can make like two equations out of it, but we could technically solve for y. What about that one? Could we solve for y there? Okay, so let's come back to our implicit versus explicit. We have a problem here because our y's, there's multiple of them here. They have exponents. Like, all we know is how to take derivatives of something that looks like y equals. Okay? That's because it is an explicit function. It's in terms of just the one variable. Okay? This is an explicit function. Y equals in terms of x. Okay? Implicit function means we have, basically we can't really solve for y in a nice way, or at all. Okay? So maybe write this down, that this is an implicit function. So when you see the word implicit, you'll understand what I'm talking about. Okay? I'm trying to compare this to your music example. Like the explicit and implicit. Explicit, you said, means nothing is censored.
Mm-hmm.
I'm not sure if I can connect to that. If anyone has an idea, let me know. But like you know, what's really annoying about the English language is that there's words that have multiple meanings, right? I find that to be kind of annoying. Especially as I'm like teaching my children how to read or like teaching them to understand words. Like, it's really confusing. Okay, so we have been looking at functions that are written explicitly, and we have been taking their derivatives explicitly. Now I'm going to present you with implicit functions, which means we're going to have to take the derivatives implicitly. Okay, so let me ask you this. If we were to take this derivative, we would write dy dx equals 9x squared minus 4. Do you agree?
Yeah.
Okay, so do you agree that when we take the derivative, if we have a y, we write dy dx? That's one of our options. So what we're going to do here is we're going to take the derivative like this as is, but we're just going to have to be careful. We're going to take the derivative with respect to x. So anytime there's a variable that's not x, like in this case we had a y, we had to write, well, the derivative of y with respect to x, we notate that as dy dx. Okay. The derivative of x with respect to x, excuse me, that's x squared. The derivative of x squared with respect to x, what is it? The derivative of y cubed with respect to x. Okay? Can we still use a power rule? Yes, we can. However, since we are taking the derivative with respect to x, and this guy is not x, then we have to use the chain rule. Okay? The derivative of y cubed is 3y squared times the derivative of y with respect to x, we have to write as dy dx. Okay? We don't do that when we have x, because dx is just 1. I've never even talked about that because it's not necessary. Okay? Well, now that we have a variable that we're taking the derivative of with respect to x, okay, we have to account for that chain rule happening. Okay. Does this make sense? Okay, if it were an f, we'd have to do the same thing and write df dx. Probably not going to happen, but any variable, that's what we're going to do if it's not x. Okay. So here's the process that we're going to take. Okay. So you're going to have an equation, and there's probably going to be multiple terms on both sides of the equation because it's written implicitly. So you need to take the derivative of both sides with respect to x, of every single term individually. What's going to happen is some of your terms will have a dy dx and some of them will not. Anytime you have a term that has a y and you take its derivative, you're going to have a dy dx attached to it. But there's going to be terms where you do not have a dy dx attached to it. So, if our goal is to find the derivative, essentially we want dy dx equals. Okay? So I'm going to ask you to separate, put all of your dy dx terms together, and put all of your non-dy dx terms together. So then that way you can solve for dy dx. I want to give you a list because I know some of you function well off of specific instructions. Okay, I understand that this might not click right now because we don't have an example in front of us. So I ask that you just be patient. Once again, this opens the door for us to have another strategy. Okay. What's going to happen when we get to Unit 3 is we're going to have to make some decisions about what to do with our derivatives, and this is just something that's nice so that we don't have to solve for y. We don't have to take that time to do some algebra beforehand. Okay? So, are you ready for an example? Okay? It's a rainy Friday. You guys are driving a little bit. Okay, write it down. Turn to your neighbor. Is this explicit or implicit? And how do you know? Okay, so I didn't do a very good job trying to trick you, right? Is this implicit or explicit? Okay, it's implicit. Dylan, give me your first reason that it was implicit. Okay, you see the y cubed, and that stuck out to you. Okay, I don't want to solve for y. Did anybody else have a different reason that jumped out to them? Yeah. Okay, there's multiple y's of different powers. Okay, so whether you see multiple y's, whether you see y with a power, those are things that need to jump out to you as, okay, this is an implicit function. Okay, it's not written as y equals, and we can't get it to there. All right, so this is what we're going to do. We're going to take the derivative. You ready? All right, the derivative of y cubed. 3y squared. However, we have to apply the chain rule because we're taking the derivative with respect to x. So 3y squared times the derivative of y. Okay. xy. What did you say? I would not use that rule, but there is a rule that we need to use. Okay. What is happening with x and y? They're being multiplied. So we need to use the product rule. Which I think is what you meant, but I wasn't. Okay.
We usually product power.
Oh, I heard.
That's what I was thinking.
Okay, product rule. We're all on the same page. All right, so the derivative of x times y plus x times the derivative of y. Equals the derivative of the right side, the derivative of 3x is, and the derivative of 1? 0. Okay. All right, so do you see how a couple of our terms have a dy dx and a couple of them do not? Okay, so this is we're going to go through that second step. Collect dy dx's together and the other ones together. So these two terms that have a dy dx, I'm going to keep them on the left side. And then, because they're already there, and so this term, 1 times y, I'm going to go ahead and subtract that over to the other side. So now everything on one side has dy dx's, and everything on the other side does not have dy dx. So now if we want to solve for dy dx, okay, the whole purpose of us collecting them together is so that we can force a GCF. These two terms have dy dx in common. So what we can do is we can factor out dy dx from those two terms. And once we have it factored out, what can I do with this chunk right here? Divide it over. Okay. I actually like implicit derivatives. You don't get as many crazy functions that you have to take the derivatives of. Like in yesterday's quiz, we had like a chain rule that we had to do 3 times, or we had, crazy product rules. Most of the time, the derivatives are pretty straightforward. The biggest thing that you have to look for would be like a small product or quotient rule. Okay. It disappeared. XY is going to be a very popular term in an implicit function. We need to keep our eyes out for that and remember that it is a product and we need to use the product rule. It's something that's very easy to overlook. All right, let's look at this problem right here. Go ahead, or not. Okay, just write x, y equals 1. Okay. This is written as an implicit function. Do you agree? Okay. So if we were to take the derivative just like this, we have x times y as a product, right? What's the derivative of 1? Okay. So we would have x times dy dx equals negative y. Solving for dy dx would give us negative y over x. Okay. A majority of the time, well, every time, you should have a derivative that has an x. At the very least, it will have a y in it, okay? But most of the time, it's going to have both variables, okay? But it will always have a y in it because it's implicit, all right? Now, do you agree that we can easily solve for y in this equation? Okay, and I didn't have my screen shade, so you already saw it anyway, right? Y equals 1 over x. Well, what's that derivative? Okay, 1 over x is the same thing as x to the negative first. Do you agree? So its derivative would be negative x to the negative second. Okay, and we've been doing power rule enough to where I think that we can think about that in our head and me writing up this up here. Are you okay with that? Yes.
Why'd you set the first one equal to 0?
The derivative of 1 is 0. Okay. So when we take a problem implicitly, or when we take the derivative implicitly, we're going to have something that involves a y. When we have an explicit function, we'll only have a derivative in terms of x. Okay? Yes? It still represents the same thing. Just what's happening is we don't have a function. So if there is a y to a power, it means we have something that probably doesn't pass the vertical line test. A very popular one, like the one on my very first slide, x squared plus y squared equals 25. That's a circle, okay? But we can find the derivative and look at where we have certain tangent lines to that circle, okay? So yeah, it's still representing sloped instantaneous rate of change, okay? We're just looking at equations that aren't functions, okay?
So how are those two?
Well, since y is 1 over x, if I plugged in 1 over x for y, we'd get negative 1 over x squared, which is the same thing. Okay? All right. Go ahead and write this down. Okay. All right. Find the slope of the tangent line at negative 1, 2, and here we have this, okay? So you see the word slope of the tangent line, or even tangent line, or even just slope, right? And in calculus, we think what? Derivative, okay? So no matter what is after it, I know that with that equation, I need to take the derivative, okay? Do we have an explicit or an implicit equation? Implicit. I see more than one term with a y. I see a y squared. Okay. We have an implicit function. It's not a function. An implicit equation. Okay. So let's go ahead and I want you to find the derivative. Work together at your pad, comparing step by step, but I want to see what you can do on this one. Just find the derivative.
Oh, yeah. Okay, but you have to make sure you like. No, it's so it's negative. No, it's 2x minus y minus x times y
Yes. So like the derivative of y squared. Do the power rule, 2y. And then you would need to multiply dy dx.
Yeah.
This is my derivative. If your numerator is negative 2x plus y, guess what it means the same thing. If your denominator is negative x plus 2y, Okay, I'm going to give you one more minute and then I'll go through the work in between. All right, let's chat about this. Okay. Here are some things that I saw as I was walking around. We did a great job with x squared. We did a great job with the product rule because we have talked about it a couple times already. However, do you see how we're subtracting? Okay, so you need to either do the product rule inside of parentheses because we're subtracting the entire product rule, or you need to view that as a negative x times y. Either way, both of those terms need to end up being negative. Okay. And please be careful, okay? When we take the derivative of y squared, we do the power rule times dy dx because it's not an x term. And what's the derivative of 7? Do you know how common this mistake is right here? It's more common than it should be, but every year it happens. If it happened to you, don't worry. Just remember it for next time, okay? So our dy dx terms would be negative x dy dx and plus 2y dy dx. Over on this side, we should have a positive y and a negative 2x. So y minus 2x is how I prefer to write it. If you write it as negative 2x plus y, does that matter? No. So then we can factor out dy dx and divide that quantity over. Okay? Any questions before we move forward? Okay. Now, I want the slope at the coordinate negative 1, 2. So we're going to take dy dx and we're going to evaluate it at negative 1, 2, which means anywhere there's a y, I'm putting a 2, and anywhere there's an x, we're putting a negative 1. What's our slope? So if I wanted the tangent line equation, you have your coordinate, you have your slope, you could easily put those two things together. All right, we have 5 minutes left. I have one more example. You ready? Thank you for actually stopping.
Pardon the interruption. Every 2 seconds, someone in the U.S. needs blood. If you are 16, 17, or 18, you can save 3 people on October 4th with 1 blood donation. Sign up outside the lunchroom today. Be kind and be a blood donor. Thank you.
All right, so let's think about this. First of all, do you see how there's a y inside of our trig function? Okay, we're not solving for y. Okay, we have an explicit function. Excuse me, implicit. I said that wrong. We have an implicit function. All right? 2 sine of x cosine y equals 4. What do we have over there on the left side?
What? A product.
We have a product. Okay? So you can do one of 2 things. You can view that 2 as a coefficient and then make a parentheses for sine x cosine y derivative, or you can view that as 2 sine of x times cosine of y.
Can't divide it.
Oh, or you could divide it over.
Yeah.
You want to divide it over? Okay. Okay. So when we take this derivative, the derivative of sine of x is cosine of x times our second function, cosine y. Nobody's made a comment about my projector. Is it blinding anybody?
Yes.
I got a new projector since the last time we've met. Okay. Plus sine of x times the derivative of cosine of y would be negative sine y dy dx. Very good. Equals, everybody, what's the derivative of 2?
0.
Who said that? Okay, so we have negative sine of x sine of y dy dx equals, I can subtract that cosine x cosine y over what?
Are you just rewriting?
Well, yeah, I subtracted this over since it didn't have a dy dx. I left this guy since it did have a dy dx. So now to solve for dy dx, we can simply divide it over. Now, we can't do anything with cosine of x times cosine of y. I know they're both cosine, but their angles are different. One has an angle of x, one has an angle of y. However, there is cosine of x divided by sine of x, and there is cosine of y divided by sine of y. Yes, the negatives would go away. And if you wanted to, you could rewrite this as cotangent x, cotangent y. That is a possibility. If you didn't, I wouldn't have a problem. Okay? But I want you to understand that these two can't be combined. However, these two with the same angle can be combined. All right. Yes, Grace.
When you took the derivative of cosine y, why is it negative sine y dy dx instead of just negative sine dy?
Well, because when we take the chain rule, we take the derivative, leave the inside alone. So like we took the derivative of cosine, but left y inside, and then took the derivative. Does that make sense? Okay. All right, you have some book work to complete for me over the weekend.